Okay, so Wednesday, and we're going to finish up on parallel circuits today. And as you've noticed from yesterday's lesson, if you have two circuits that are in parallel, fairly easy to figure out all the voltages and the currents that are associated uh, with the circuits. Okay, but now we're going to actually make it a little bit more complicated by adding additional parallel circuits to it. Okay. Remember, think of your house again. How many parallel circuits do you have in your house? How many breakers do you have in your breaker box? Okay, so that gives you an idea of how many parallel circuits you actually have. All right. Okay, so this is we'll start off with multiple parallel circuits. Okay, you can take the long road and figure out the currents in each of the legs or the banks of the different circuits. And then you add all those circuits up, all those currents up to give you a total current that has to be supplied by the supply voltage, right? That's fairly straightforward to do. Okay, but when you get a little bit uh, more complicated, that is, you have more, the more you add, the more you have to more math you have to perform. Okay, one of the best approaches is to actually use the equivalent resistors, equivalent resistance of a circuit, of a parallel circuit. And I think I gave you yesterday the equation to use that for resistors that are in parallel with one another, we use the reciprocal summation. That is the 1 over the equivalent resistance, total equivalent resistance is equal to the sum of 1 over the individual resistances. So 1 over R1 plus 1 over R2 and so forth. And I showed you how to do that, or I told you how you can do that easily using your calculator. And all you have to do is use the x to the minus 1 key, okay? Use it smartly, and you'll get the result, R equivalent, very quickly. Instead of taking individual resistance values, converting them to conductance values, summing the conductance values up, and then taking the total conductance and take the reciprocal of that to figure out what the R equivalent is. Okay, that's the other way of doing it. That's the long way of doing it. Okay. So that's as far as we'll take that, okay? And you're going to complete all the homework, and then tomorrow we'll go over all the homework with parallel circuits, and the following day we will go over, or tomorrow we'll also go start series parallel circuits, where we have a combination of series together with a combination of parallel circuits. And one of the things that we should learn from the parallel circuits is that there's always a way of reducing the parallelism. That is, we can get an equivalent. If you have two circuits that are in parallel, we can create an equivalent series circuit out of that, okay, by combining those two, the resistance of those two paths, of the two parallel paths, and getting an R equivalent. Then by getting an R equivalent, we divide the R equivalent into the voltage to get a total current. But after you figured out the total current, then you're going to have to figure out what the individual currents are for each of the two parallel circuits. All right? So that's the other way of doing it. But we'll see though that once we get to series parallel circuits, that is a handy tool to know. Okay, a handy way of solving more complex resistor network circuits. Okay, so we'll get going on that.